Hello everyone, I'm Wang. I will introduce our work scaling data generation in vision and language navigation for you. This is a cooperative work with Jialu, Yicong, Yi, Qi, Mohit, Steve, Hao, and Yu from the ENU, Shanghai Lab, UNC Chapel Hill, University of Adelaide, and Adobe Research. Vision and language navigation requires a robot to do visual navigation for the natural language instructions in previous sensing environment, as shown in Figure 121. VLN suffers from a data scarcity problem for a long time, as photorealistic 3D, room scans, and also human instructions are both very expensive and hard to collect. And this leads to that we have very limited environment and also human annotations to learn VLN agents. And as a result, there's a long-lasting scene-enhancing gap problem for VLN, which means the agent performance in validation scene split will be much better than agent performance in test and scene split. There are some methods to try to close this gap. They may either do some modification to the training environment or introduce some new environments, but the gap still remains very large. In this work, instead, we introduce scale VLN data generation paradigm that we first get 3D row meshes from HM3D and Gibson environment dataset, and then we build navigation graphs for these environments to fit VLN setting, and then we recover the faulty render images to be more photorealistic using a commodulated GAN. Then we sample out paths from the graphs and also generate instructions for this path using a prediction speaker. And in the end, we pre-train our agent with scale VLN incorporated and then fine-tune them on other downstream tasks. In our experiment, we used two state-of-the-art VLN agents to test the effectiveness of our method. The first is dual-scale graph transformer, DUS, and the second is history or multimodal transformer, HMT. We pre-train our agent with single action prediction and master language modeling as the objectives on scale VLN, prevalence, and room-to-room datasets, and then fine-tune them using imitation learning on downstream tasks. Here is our main result. We first explore how to utilize the scale VLN dataset. We found that incorporating scale VLN dataset in both pre-training and fine-tuning will usually improve the agent performance, while pre-training with both prevalent and scale VLN, while fine-tuning with only scale VLN as augmentation dataset works best. And also for the room-to-room task, the performance of a state-of-the-art agent DUD could be improved by absolutely more than 10% in success rate by incorporating with scale VLN from less than 70% to more than 80% and approaches human-level performance for the first time. And another exciting thing is the scene-enhancing gap could be naturally bridged by using scale VLN's environments and data to less than 1% versus usually about 10% for previous method. We could also achieve state-of-the-art performance on other downstream tasks, including REVERIE, CVDN, and room-to-room CE. We also explore what really matters when scaling VLN data. We found that both traversable graphs, photorealistic images will improve downstream performances, while adding more scenes and data consistently improves downstream performance. In summary, we introduced scale VLN data generation paradigm that generates more than 1,000 traversable, multi-view consistent, photorealistic, interactable VLN training environments, and also about 5 million instruction try to parse. We studied how to properly utilize scale VLN and what really matters in scale VLN in our experiments. And we could achieve state-of-the-art performances on various VLN downstream tasks. And also we could bridge the scene-enhancing gap for the room-to-room task. That's all, thank you.